Okay.
Okay. Need to get to. Okay. So we're looking on lab 21, we're trying to fix.
Oops, wrong folder.
Correct. Save it. Excellent. Get add Jim. Okay, it should be fixed. Let's verify that. Trust but verify.
Thank you.
No, it's still pointing to the wrong place. Piece of crap. It did not take my input. Oh, it's cached, I bet. That's what the problem is. Huh. All the changes. Delete that one. Yay, now it's fixed.
Good.
Looks like you can start.
Okay. I just need to be able to share. If I could get the screen share or the host, then I can
Oh,
go
that
ahead.
would make your life a lot easier.
Yeah, it would.
You should be able to do it now.
All right. Let's see. We want this one. And we want the chat box.
Is it working now?
I can check myself. Yeah, that's different now. Before, when I would hover over it, it said 21 take home. Okay, then. Today, we're going to be doing some probability estimation modeling. That wasn't obvious by the title. All right. Now, if you're following along, some of these cells I'm writing as we go, and you'll have to fill them in with what I've done. But yeah, let's go ahead and get started.
It's still coming up as 21 take home for me.
Refresh your browser.
Now, this is the correct one. When I click this one's correct, and this one is take home. They have a different different name here.
So when I go on the take home, I click.
Refresh your browser.
Yeah, I already did that. And then I do save as, and then it still comes up as 20 lab 21 take home.
I guess you can't see my save as window now, but it is lab 21, the regular one.
Yeah, I don't know what's happening with mine.
I could
the link.
toss it.
The link is fixed. If it's not working for you, it's your browser's cache still has the old crap in it. You're probably using a Windows machine. Worst case, you'll have to exit and restart the browser.
I'll slap it into
Okay.
the chat box.
Thank you.
All right, lab 21. Okie doke. All right, where was I? Okay. So a couple of important things we need to get out of the way are some terms. First one is our population. So in statistics, the population is the entire pool from which our sample is drawn. It could refer to an entire group, people, some group of objects, events, hospital visits, or measurements. The sample is the set of individuals or objects collected or selected from a population by a defined procedure. The elements of a sample are known as sample points, containing sampling units or observations. And so our data model then is a function or a listing which shows all the possible values of the data. It also tells you how often each value occurs. So what does any of this mean? Well, let's take all the students at Texas Tech, however many there are. That is the population. We want to figure out what is the, I don't know, maybe we're doing a health survey and we want to know the median, not median, well, that too. All the nice information about everybody's height, weight, blood pressure, stuff like that. And we're going to do that for men and for women. Well, that would be really expensive to do if we did every single person in Texas Tech. So we're not going to. What we're going to do instead is we're going to take a sample. Now, how do I take this sample? How do I make it a good sample? Am I going to go down to the sub and find the first 5 people that are chowing down on 10 Chick-fil-A sandwiches? I could, but that would drastically influence the way my study is going to go, because what my study is going to say is we took a random sampling, and this is supposed to be representative of the population at large. Well, how did you take your random sampling? Well, I went down to the sub, pointed at some people. Well, that's not very good random sampling. What about if I go to the rec and ask people, put up a big sign, hey, I want to talk to people and get their health measurements? Well, that's also kind of not great, because that introduces what's called a self-selecting sample. What that means is I advertise that I'm doing a study and I want people to come participate. Well, the people who are more likely to come participate in the study are the ones who are interested in that field. You see this all the time. So if this particular study is about health, the people who are interested in health are probably going to come volunteer to study. So again, our random sampling is not super great. It's not representative of the population at large. What would be a good way to do it? Well, the best thing you can do is get the entire population. Well, since we can't do that, what you would want to do is, as well as possible, pick a random grouping of people. But that's not always as easy as it sounds. Okay, so we have some data. I've downloaded it. File looks a little strange because I'm not sure what PKF is. But here's the data. And what is this data? Well, it's an actual WATStor formatted file. Never heard of that. For a gauge at Spring Creek, Texas, the first few lines look like this. What are we wanting to do? We want to estimate the magnitude of the annual peak flow at Spring Creek near Spring, Texas. So we have a waterway, and we want to estimate the magnitude of the annual peak. It's out. I guess before we go any further, it's important to keep in mind the steps we're trying to do here. Once we have our data, we want to get the descriptive statistics. So the standard deviation, variance, and mean. From those, we can do pretty much anything we want. Use plotting position formulas and plot samples, and plot the samples from the data we already have. We want to use different data models and find one that better fits our sample, visually or numerically, as we discussed last session. And then we want to use the data model that has the best fit. That way we can predict in the best fashion. All right, so our file kind of looks like this. Here's another glimpse at it. It's a whole bunch of stuff. I'm imagining that at least this is the flow we're interested in. Okay, well, I could have just read a little bit further. The first column are some agency codes that identify the station. Second column, after the fourth row, is a date. Okay. Third column is a discharge in CFS. The fourth and fifth columns are not relevant for what we're wanting to do. The file is downloaded from here. In the original file, there are a couple of codes that are manually removed. So some stuff that we didn't want to look at. What we want to do is fit our data models to this data, decide the best model from visual perspective, and report from that data model the magnitudes of peak flow associated with the probabilities below. Probabilities. Huh. All right. So what we want to be looking at is the exceedance probability of 25%. So that's a 75% chance or greater. And same thing for 50, 75, and 90. And then we get into the 99, and these are the exceedingly rare. So if you remember, let me get my annotation tool. Remember when we have, at least for a normal distribution, we say, all right, here's the mean. And then 68% of all values fall in from the population fall in this window here. So 68% of everything that goes on falls in here. Okay. Well, 95% of all the stuff that happens in our whatever we're measuring is a window of 2 standard deviations. So everything that falls in here inside the new window. So that's 95%. 95. Well, we have these exceedingly rare ones that if we go to a third standard deviation away, this gets us 90, like 99.5% of everything. So everything in here is almost everything. The only things that fall outside are the outliers. And so if I were to do a 99% confidence interval, essentially what I'm saying is everything outside of that are, we'll call them one, so it's the storm of the century kind of thing. If I go to 99.8, this is kind of a 1 in 500 year chance. If I go to 99.9, this is once in a millennia kind of event. Think of, I can't remember the name of it. There was a volcano. It wasn't Krakatoa. It was one in the Indian Ocean. I think it's the largest on record. That's a 1,000-year event, at least as long as we've been recording volcanoes. It's an interesting field because how are you supposed to record all the data points about something that happened in 1688? Who knows? Actually, there are ways, but another story for another time. Okay, so I had to go look for some, this is some simple code. We want to download the file. It's at the web root, and this is the file we want. And this wasn't here. So I went and looked, I think, in like lab 16 for the code to go do it, because I don't remember it off the top of my head how to do the requests. So I just got the web root and added the file name and downloaded it. So now we have it. And then from there, we're going to do the data frame stuff. We want to put something into a data frame. That's what we work in. Data frames are nice. But before we can do that, you notice that this is a little wonky. So how do I get the numbers I want? So it's going to be these and these and these, but I don't want all this stuff. Okay, so what am I going to do? Well, we're going to get rid of it. I'm going to make a matrix. It's going to be empty. It's going to be storing stuff. The columns we're interested in pruning, we've got column 0, 1, and 2. We're going to read in our file. And notice that we are looking at the lines after line 4. How do we know that? Well, I'm reading all the lines, and I'm using this index notation to say everything from, which would be the 5th line, onward is what I want. All right, we've done that. Disconnect the file because I don't want to have it open all anytime. Get how many rows we have, and then iterate through all those rows. And we want to, all right, so we got to read this kind of back to front. What are we doing here? Well, the ith row we're on, we want to get rid of any spaces and stuff that we don't want. First, what we're going to do is we're going to split. Then we're going to strip anything that is not necessary, and the strip function by default will just get rid of like white space and stuff. And then now what we had was a line, and now that we've gone into this and split it, we have a collection of lines. So we're going to append those to our first matrix. All right, and we're going to do that for every row. And then after we've done that for every row, we're going to go in and cast the column 0 as an integer. Cast the, what are we doing here? Okay, so we cast the first column as an integer and throw it into column 0. We leave the second one alone and throw that into column 1. And we cast the third one to an integer and throw it in column 2. All right. Now we have what we need. We can build our data frame. So we're going to bring in pandas. We're going to make a data frame out of column 0, and we're going to add some columns. Columns are easy to add. Rows are hard. So that's why we did it that way. Okay. So after we've done that, we can use the head function to look at some stuff. We also have the describe function that does things. How many are in there? 80. What is the mean of the first column? Well, that's a big one. But remember, it's kind of this weird ID station kind of thing. We also have date and flow and all the stuff we're interested in. So I want to see this one. Oops. I want to see this one again. All right. I was just making sure that date was still there because it wasn't showing us the date in there. All right. So now we can plot the data frame as a plot of peaks versus date. Okay. That is something we can do. And I want everyone to pay attention to what steps I'm doing here, because they're not all, as you can see, they're not all here written in. We're figuring them out as we go. And your take home is the same thing. It's just you're looking at a different site. So it will behoove you to follow along. So I'm going to look back here because I don't remember the syntax off the top of my head. And well, that's not a big deal. So we want to plot a data frame as peaks versus date. Well, that's pretty easy. If we don't remember the syntax, we just Python plot data frame, and off we go, if I could spell. Now, there's a bunch of ways to do it. Let's do the data frame.plot, look at an example. I guess it isn't going to give us a full example. That's fine. We could look in a previous lab to find it, but I think we're just going to try doing the data frame.plot. All right. What was the syntax for that again? Data frame.plot. Okay. That's what we want. Go back to our code here. And what do we want to plot? Well, we're wanting to plot our data frame called df. And we are wanting to also do plot of the peaks versus the date. Okay. Now let's do it a bit at a time and see where we get. Okay. So right now we are plotting the flow. So and the 0th column. But the problem is the 0th column is a whole bunch of strange numbers, and we don't want that. What we want to plot is the date and the flow. So now that, oh, someone's already posting stuff. I wasn't paying attention to chat. So the question was, at the top, I saw you get 60-44 or something like that, and you got 274. The 60-44 is a 60-22. It's just like a code that's printed out when something successfully works. So I wouldn't worry about that. This number isn't really part of the data. It doesn't surprise me that your machine gives you a different. Oh, it's the record count. Okay, cool. Oh, well, I didn't know that. All right, and so Ethan posted some code here, and I want to see what it does. So let's try that. So what did we end up getting? So we go with the first df.plot. Df is our data frame, and we didn't give any arguments. And what do we get? We got the first two, or the interesting thing is we got the the ID for the stations and the flow. And that's what was plotted. Well, that's not what we want. What we want is to plot the flow and the date. So let's try seeing how he did it. Okay. Well, let's read through this. We've got our matplotlib and our numpy. Those are good if we're going to be messing with series. So we look at our data frame. And remember with a data frame, instead of having to say column 0, column 1, we can say the date column, which is the name of this one, and the flow column. Now, interestingly, one of these actually is labeled as 0. So we could do that if we want. And then we're going to plot. So make the figure size something. And what are we plotting? Well, the arguments we're handing it are date, flow, and the last one is color, just because we can. I can try to make it something else. If that's an actual one that's loaded in. It is. All right. So the it is a little hard to read though. Okay, let's go back to blue. So what you can see here is we have the x-axis as the first argument, y-axis is the second one, and I'm not entirely sure what that's measured in, probably liters or something. Did it mention above? Discharge in CFS. I'm not entirely sure what that unit would be, but it's water. So it's something like, liters per second or something like that. So the bottom one, it's a little hard to read because they're all smushed together. I don't remember the argument to turn it vertically or horizontally, but we could look it up, but it's not that important. But what we can see now is that from when this is started, the data recording started, you see the measurement, and as it goes on, you can see that, unfortunately, I can't exactly tell you what date it is. We had let's see, let's look at the actual stuff. So 1942, 1929 to 2017 is when this is done. So it's almost 100 years. So we had two outliers here. One so this is 1929, this is 2017, this is, I don't know, 1980 something. So 1980 something. And we could actually look this up in there and going into the data frame, but we're just looking at the plot. Okay. Now what can we do? We want some descriptive statistics. What do you guys remember descriptive statistics as? It was actually in this, oh, it's cubic feet per second. Okay, makes sense. What do you guys remember descriptive statistics as? Of all the things we've talked about, there are, so like probability density functions, you've got your standard deviations, you've got your least squares method. Of all those things, what are called descriptive statistics? Now, the name itself lends something to it, what we're talking about. Yeah. So your means, your percentile, standard deviation, all that stuff. It's the things you get when I do this, df.describe. Execute. So the stuff we get here, your maximums, your standard deviation. I think this misses on mode, but we don't use that very much. We've got our percentiles, and the first one isn't really worth paying much attention to. In fact, we might be able to do this. I'm not sure, but because it's a series, it's no longer a data frame, but we'll see. Okay, it does, which is nice. So we've used the describe method on flow, which I probably should have put down here. We want descriptive statistics. How do we get descriptive statistics? Well, there's some. What are the ones we're interested in? Do you guys remember from above there were the scaffolding of what we're wanting to do? I think there were 3 that we really want. So are those 3 accounted for here? Well, let's go look. What were the ones we're wanting? We want the mean, the variance, and the standard deviation. Do we have those? We've got the mean, the standard deviation, and we don't have the variance. So what do we need to do to get the variance? It's not printed, but it's somewhere in there. We could square the standard deviation. That's a good one. We could do that. I think we can also do this. Yeah, we can do that. It's not actually shown in the describe, which is a little strange, but that's fine. What I'm going to do is I don't always remember the syntax for the variance. I kind of just guessed on this one, and you know, it's pretty straightforward. But what we're going to do is make some variables. So variance, I'll even call it the flow variance. All right. So we want that one, and we wanted the flow standard deviation, and we wanted the mean, right? Mean. Okay. So we could access this from the describe because it gives us a some series to print, but we can also do, I'm pretty sure it's just std, and this one is flow.mean. And I guess I could print them out. Print flow variance. I'm going to call it fair because 1, I can't spell, and 2, it's smaller. So print that, standard deviation, and the mean. All right, mean and the standard deviation. All right, we got them. Does this look like this squared? Well, it's a 15, and I do remember my multiplication tables. That goes to 225, and there are a whole bunch of decimal places here, and that's the double the number of decimal places here. Seems straight enough to me. And the mean, I'm just going to trust that it's mean. I don't have any reason to doubt it. Okay, so we got some descriptive statistics, at least the 3 we were wanting above. Now what we're wanting to do is the scaffolding above, we wanted to try some position plotting formulas. So we've got 3 of them. I haven't used them before, and I'm pretty sure you guys haven't used them before, unless you count the lesson today. But let's actually run them and see what we get. So let's look at the lecture. Oh, lecture. Duh, I'm in the wrong one. I want this one. Yeah, I had the lab open because we were talking about the issues. So we're wanting to do what's it called? Weibull. We're gonna look that up. All right, this is where we appear to be. So, as has been said a million times before, I'll go out on a limb and say probably the most important skill you can learn in programming is what and when and how to copy and paste. Because, well, here's a great example. I am not going to go and write the algorithm for the Quantile approximation. Why? Well, 1, I don't know the theory behind it. I probably would do a poor job, even if I did. This has been optimized and looked at, and it's in a library that is designed to perform. So why would I reinvent the wheel? Well, sometimes you have to tailor the wheel to what you want it to do, but very rarely do you want to reinvent it. So what are we going to do? The all-powerful Control-C and Control V. I might be able to get all of it in one. All right, where were we? We were here. Okie doke. Now, copy and paste gets us a long, long way, but doesn't get us everywhere. Now, it is wanting a sample and a variable called sample. So let's see. That is just a random sampling of stuff. And from that random sampling, we get the mean and we get the standard deviation and we get the variance. So instead of using those, we're going to be plugging in the appropriate values from what we've got going on. Okay. Now, can someone tell me, and it's okay if it's incorrect, we're in the art of copied and pasted, and I know the kind of thing that is here because I just looked it up, and I know what my version of that thing is, and we're going to plug it in and see if it works. What kind of thing is sample? Is it an integer? Is it a list? What is it? You can find it. Oh, wrong one again. We can find it here. Here's the definition. Okay, so you say it's an integer? Well, let's find out. There's a very easy way to find out. I'm pretty sure that's already imported, so we don't need it. So we want to figure out what the heck is this thing, because I want to plug the right thing in. Well, so if I do that, oh, I guess NumPy wasn't in. Import NumPy. Okay. So what kind of thing is sample? Well, let's look at it. Interesting. It appears to be a NumPy array. Do you guys remember we have a name for that? It's the kind of thing that goes into a data frame as the columns. Do you remember what that is? I think this might work. I don't know. No, it's the other way around. Probably gonna tell me NumPy array. Yeah, it is. Series, yes, very good. So we have some series here, right? We're plotting two of them against each other. We've got the date and we've got the flow. Which one do you think? So we're in the business of predicting. Let me ask the question this way. Remember last lecture, we were talking about things in terms of a predictor value and or a predictor variable and then the output variable. Which one? We have two here. We have date and we have flow. Which is the predictor and which is the output? Is it the flow or the date? Flow is the output. Okay, that's correct. Which means that date is the predictor. Are we in the business of predicting the date? I mean, maybe if we're doing some kind of time travel thing, but I don't think we're in the business of predicting the date. So we must be in the business of predicting the flow. Sure would be nice, or future sales. Yes, exactly. It sure would be nice if we had, so sample, remember the thing we just messed with, is a series. It sure would be nice if we had a series of flow. Oh, hey, we already do. So just to belabor the point, type of flow. Oops. So one's a series and one's a NumPy array. Those are the same thing. So as far as we know, you can just replace everything with flow. And let's see what happens. Might not work. But that's kind of the magic of how this stuff goes. You plug stuff in, see what breaks. If it works, cool. If it works and you're surprised, now that's an entire different lecture. Okay, what did it not like? Series object has no attribute sort. Okay, so we want, even though the NumPy array and the series are used as the same thing, there appears to be something it doesn't like. Just for, all right, doesn't like that either. Okay, so let us see what sample actually looks like and see what flow actually looks like, because we can get one out of the other pretty easily. So that's flow. And that's sample. All right, so all we got to do, Python series to NumPy array. Okie dokie. Well, that seems pretty straightforward, don't you think? Dot to underscore NumPy. See what that does. Get a dot there. Hey, that looks better. All right. Oops. Yeah, I didn't. I did the method, but I didn't store it as something. So we want to say flow array. Sure, that works. And just for the heck of it, type of flow array. All right. So that's the same type as we had before with sample. So let's plug that in here. And I think there was one more. There it is. All right. Now we don't like name YCDF is not defined. That is correct because I haven't done that. Now, what is YCDF? Question one, do we need it? It's trying to put, it's the fit. Okay. So where is YCDF defined? Let's find out. YCDF, okay. It is an empty array. Oh, it's the cumulative distribution function, duh. Did we do this in the other one? I don't think so, but we can sure do it. It doesn't take much. All right. Are we? What we are missing, I believe, would be the line that goes through them. Let's take a look at what the lab does for the Y bull would be here. And the red line is the thing we're missing. So let's do some of this. And I think I'm just going to try this. I don't know if it'll work, but that's often things you do. We want YCDF is, we know it's an array. It started out empty. Let's see what happens when it's empty. Okay, X is not defined. What was X? See the definition for it. It's another empty array. Okay, we can work with that. All these are going to be fitted in the next section, so it's not a big deal. All right, so this is a one-for-one recreation of our first attempt at the Y bull. It looks kind of weird. Well, let's fix it. Let's fit some stuff. Okay, so we'll make a new cell. And now those pesky X's and CDFs, we're going to make them look nicer. Now we did use the magic tool of copy and paste. So let us plug things in as we go. All right, so the standard deviation, no, we want the variance. Now I took the variance of the flow series. I'm pretty sure that even though I turned it into a NumPy array, it shouldn't matter. If it does, well, we'll figure it out. All right, variance goes there, and the mean goes there. Mean, all right, what else? The X high and low are defined here. So I don't believe that this is going to be what we want. I believe we want to actually get the minimum and the maximum and the count. Does anybody remember the methods for those? I think it should be pretty easy. Flow, not min, maybe. I can test it. Let's see. What is print? Well, I don't need that right now. Because they're listed here in the describe. So let's find out. Let's see, flow.min. All right, seems pretty useful. Let's just try the max. Also good. And the other one we want is count. If I can spell. All right, they all seem to be the same name they are in the description, which is good. All right, so let's go and plug those in. So flow.max, flow.count. And the only thing that could possibly go wrong, well, what a statement that is. Remember, I got these values from the series instead of the NumPy array. I don't believe it should matter because they're just numbers. They're floats. All these are floats. And so I don't think that should be a problem. All right, so what else do we need to look at? Go through the array. So can anybody tell me what we're doing here? What we've seen that before. What kind of thing are we doing? We're doing some kind of step-by-step algorithm. We did it a whole bunch last time. And I'm sure you did it today in lecture. We're doing a stepwise approximation. So you can see what's the high, what's the low. We're going to get the difference and we're going to divide by the occurrence. Kind of like last time when we did least squares. We're not actually taking the square of this though. All right, we're going to put that into our X. We're going to use the normal distribution to take the low value, add to it the step, and we have the mean and the standard deviation. I'm sorry, the variance. All right, let's see what happens. Name math is not defined. Okay. We can fix that. Name normal distribution is not defined. Okay, we can fix that too. Where does it come from? Where does it go? Let's see, which import do we need? We have that one, we have that one. Oh, it's function. Aha. All right, we'll make another. I can put it here. All right, functions are defined. Okay, now we have stuff. We have stuff in our X, we have stuff in our YCDF. How do I know? Well, let's print them out. X, there's some stuff. Started out empty. How do I know it started out empty? Because I made it empty. What about the YCDF? Well, let's look. YCDF. Hey, it's got stuff in it too. So let us run this again. And I don't want to delete my nice and new. I think I can just do this. Hey, that's a lot better. That's better than what we had before. What did we have before? An empty box. We had nothing. So we've got this approximation. That's the red line. And what is it? It is the calculated cumulative distribution function of your the flow going into this plot here. Interesting. You can so I guess let's ask the question. Let's go visually first. Is this a good plot? Now I'm going to change the labels while you guys answer that. This is going to be not so much. Why do you say not so much? Is it too far off in one direction, too far off in the other? So this is going to be the flow in cubic feet per second. Okay, there are many residuals and the left hand is far off. Yep, that's pretty well put. So if we try to just, I'll use the stylus. If we try to draw our own fit, our line of best fit, I don't know, let's use this one. Well, the left parts here aren't very accounted for, and we're off quite a bit in our uptick here. So it starts up too quickly, and then it doesn't go quickly enough when it needs to. So it's something, but could be a lot better. So let's try a different method. Oh, I left the line on there. All right, let's get rid of this because that's annoying. Okay, let's try doing the normal quantile function. So let's go look. Oops, I think we went too far. Control F is so nice. Okay, so this is where we were. All right. We have our fitted model. And we have the line. All right. Let's try doing this one. We'll make a new cell. Wait, am I doing the right one? Fitting the data. Okay, yeah, let's try this one. Let's try this one. Okay, we've got to make sure we get the correct things in here. So we have flow, right? I think that would, what we're doing here, we're getting the mean, which we already have. That's fine, but this is the other way, I suppose, of turning our series into a NumPy array float. All right, that should work. That should work. It's another way to get the variance. Works for me. All right, low, again, we can replace these as we had before. And if it is, should be in the same format. All right. We want to use the normal distribution. Everything looks fine there. Seems to be the exact same thing we just did. I may have, well, let's find out. Does this work? All right, what's missing? X and Y must be the same size. Okay. Wait, X and Y. Where's Y defined? Y is that's kind of strange. We got the X, we got the Y in the same color. Oh, that's weird. Still try to plot it. Well, let's check out the size. So the X, and it's going to be X and Y CDF. So what's X? Stop doing that. I want to see what X is first. So I will do this. Okay. All right. Length. All right, 81. And what is YCDF? Oh, there's some questions in the chat. I'll look at it in a second. So they're both 81, so it's a bit strange. Let's address the questions. Let's see. Yeah, it's function that's defined in the lesson. Yeah. Oh, this is just the normal distribution. Yeah, they are found. Both the normal, they were up here, right here. So I guess it's slot 6. If slot, I guess I don't really know. Cell. Okay. So where were we? So they are the same size. It's a bit strange though. I might be reading the wrong error. So it's saying when I call, okay, Weibel sample color. All right, what is this one? And let's see. This is probably the issue if it didn't get built. It is print me that. Okay. Now I want to also know the length. 80, so it's missing one. Interesting. Very interesting. All right, where's this defined and what makes it? All right, look for the one before. It's defined here when we do the actual method. It's curious. So print length of Weibel. I guess we don't need that, do we? And then, yeah, do that. So it's 80. Print the length of X. 81. Huh. So what is your issue here? X and Y must be the same size. Okay. Okay with that. Did I miss putting? Yep, I sure did. I didn't put sample in. I didn't replace sample. So I don't think this will work because this needs to be the series thing. But oh, never mind. Works just fine. Okay. All right. So we fitted that, and it looks pretty much the same. We fitted data to the normal model. And this is using the Weibel, well, it's using the same method, so obviously it's going to look the same. And we've already agreed that it's not super great, so let's try doing a different method. We have the log normal quantile function. Did we have one of these charts before? Okay. So the normal distribution model, what are the difference between it and the log normal distribution model? So 75% chance. These are all pretty much the same. So let's go look at the log normal quantile function that we have from the lesson today. Okay, that's the code, but I want, oh, that's funky looking. What I want is, all right, here. Another data model we can try is the log normal, where we stipulate that the logarithms of the observations are normal. The scripts are practically the same, but there's an inverse transformation required to recover original value scale. Okay, so if we remember back to yesterday, when we had, not yesterday, Tuesday, when we had an equation of stuff, we had something over on the left, obviously, because it's an equation, but then we had this e to the x thing. And what I did is I took the log of both sides. Well, we can try to do the same thing here because in just the normal distribution, we didn't get something super nice. So let's try taking logarithms instead. Okay. So here is the same code we want to be using. We're going to be replacing at least I don't believe this is the same creek, is it? No. No, this is Spring Creek. All right. So let's try the replacement stuff we had to do before. Okay. This will put things into a list, but we already have that. So we have our NumPy array for our flow. So we don't really need this that much. The sample mean, I'll just do this, what do we call it? Flow array, I think. This isn't, I'm gonna run this and we're gonna get errors, but I'm just making sure that this isn't an error because it usually points to the first error. Yep, that's fine. Okay, so just to make sure, and we already have the sample variance means, we want to sort them. We want to build this. We're not using this anymore. We're using this. Sample mean. We already have that. Oh, defined here. Variance defined here. Make these, make them empty. Log sample, that's fine. How many? This is what? Flow.count. Same thing here. Oh, it's already defined. Okay. Normal distribution. Step. Okay. There was one more thing. Huh? Well, let's see what happens. Okay. These are the same blue dots. They're just smushed a little bit. The scale goes from 0 to 1, 0 to 1. It's just smushed. So if I were to take this box and just shrink it on the x-axis, but leave everything else alone, that's what we have. So I wonder if I can change that because I want it to be the same. What would we call that? Is it the resolution? Let's look. What library are we using here? We're using matplotlib. Change width plot. Big size. Okay, that'll work. Let's try that. What do we have before? 10 by 5? I think that's what we had. Yeah, it's right here. And then we get the smushed one. Oh, well, there's the numbers right there. I'm just blind. Okay. All right, now it's not smushed. So we tried the log normal quantile function. Did we use this anywhere? Yeah, we used it there. Okay. Want to make sure, because this looks remarkably similar to what we had before. Does it look different at all? I don't think so, which makes me think it's not getting the right thing. We're reconstructing it. Let's check the lesson to make sure. Variance is the same on both. Yeah, it does seem strange. So we copied this straight. What we want to do is see. Ah, I see what it is. I know. So that wonderful copy and paste we did. Remember I warned you about the dangers of it? Well, I replaced this whole thing, which is the array itself, but it's also having the logarithm function applied to it. So we didn't do the thing we were wanting to do. So this would be, I think we can just do this. I think that is correct. Hey, look at that. So yeah, copy and paste is your best friend and your worst enemy at the same time. So what would we say about this data model versus the one we had before?
It's the inverse.
The inverse. What do you mean by that?
Like it's flipped around. The
Okay, yeah, I can see that.
inverse function, isn't it?
Right. So the reason it looks that way, you might think that it kind of goes down towards this way. It's just because a logarithm always does this weird up and down thing as you approach 0. And so what we've done is we said this part of it, this part of the logarithm, there's nothing we can do about. It's just going to go that way all the time. But what we're going to say is, all right, I'm going to take the parts that I'm interested in, which is this part of the logarithm, and see how we can make it fit. But that's an interesting thing that you noticed. So if we're looking just at this section versus, let's say, use a different color, and I'll have to scroll back and forth, unfortunately, versus this section, which one we think is better? I kind of like the second one. I think it is visually, seems like it fits better. And I see you guys are tending to agree. There was one other thing in the logarithmic that I want to try, and it's using the anti-log. So let's see what that does. Right here. So kind of like what what you noticed about what did you say? Inverse function. That is because we're in log space. Well, what does that mean? Well, you notice how the blue dots, they aren't at the same points. So let's look at the first one. So in the 0, we had a value of 6, but well, that doesn't make any sense. We had what is our y ranging in? It's going from 0 to 12. That's weird. Why should we 0 to 12? It should be in like thousands, because we transformed everything into log space. What does that mean? Well, I took my first one, which was, I don't know, 600 something, and I took the logarithm of it, and now it's here instead of where it should have been. And same thing here. So both the red line and the blue dots are in log space, which means, all right, let's say I have, I don't want to spend too much time on this because I want to get through it. Let's say I've got some points, right? Well, and I've got a line, right? I'm going to do something weird. I don't know why I'm going to do it, but I'm going to take every single thing in this plot, so the point and the line. I'm going to apply the x squared function to it. So it's going to move stuff. They're all going to move kind of in a weird upward. You know, the further they are to the right, the further they go up, and the line's going to look like that. Why did I do that? Because now the first one we were just in our normal space. Now we're into the x squared space because I've done x squared to everything. This is the log space because we've applied the log function to everything. Yes, we are applying a transformation. Very good. It's a little more than that because you're getting my linear algebra feeling started up. Yes, we're applying a transformation. So let's unapply that transformation. All right. It was here. Kapow. All right, let us make a new cell. Unlog everything. Okay. All righty. Now, what I'm not going to do is do the wrong. I think that should work. All right, simple sort, simple mean. Where are we getting that? It's not defined. So what I will do is flow dot mean. Okay. Sample variance. I'm sure these are using the ones that are defined up here, but I just want to be. Surely it'll be fine. All right, that's the same one from above. Don't need to replace those. Don't need to replace those. All right. I think that might, I don't know. Let's run it, see what happens. All right, we're no longer in log space. I'm going to change these. Cubic feet per second. All right. And that should be good. All right, now what does quantile value mean? Well, it means pretty much exactly what you thought. This is right about here is the first quantile, so 0 to 25% of everything. Here is the second quantile, up to 50%, so on and so forth. So what do we have over here? Well, at the very edge of, this is probably the 99th quantile, or is that the right word? We have the biggest event. Remember, these are sorted as the measurement and flow as opposed to date. So this is not where that's the reason the x-axis is. It's what is the magnitude compared to everything else rather than the date. We could unsort it, but not exactly what we're interested in. Okay, so we've come out of log space, which makes everything look wonky. And we're looking at this. I think just to make things, this may be my doom here, but I want to have everything all on the same page, or closer at least. So let's try doing that. Okay. All right, do this. And there's one more thing I want to change, 10 by 5. Okay, and I'll do that. All right, that's pretty good. So which one do we like better? This is the normal distribution. This is the log normal. Data model distribution, same thing. So, well, that's not true, but for our purposes, it is. Which one do we like better? Just visually. The log norm? Yeah, me too. I think it's better. Okay, that's pretty good. If we can get any better, I'll guess we'll find out. So we got another one, and we've got about 14 minutes left. So we're doing the same thing every time. We're just using a different transformation. I'm glad you brought that up, on the data and the fit line as we do it. So let's see if there's anything. Okay, so and as I said before, the homework is the same. You're going to be doing the same stuff, exactly the same stuff, except you're going to have a different data set. You're going to be looking at the Yano River. I'm trying to think if I know what that is. I don't. So you're going to be doing the exact same stuff. You're just going to be using a different data set. So we've gone through and kind of painstakingly figured out, okay, what's the difficulty here? Well, the difficulty in all this was figuring out what to replace in our copy and paste. Because, again, why am I going to ask you to go out and derive the equations for the Gumbel EV1 quantile function? You guys are freshmen, right? How many levels of calculus have you taken? You're going to run the partial differential equations to get this to be the correct cumulative distribution function? I think not. I think that would be a little unrealistic to expect of you. So what are you going to do? You're going to do the same thing any of us do. We're going to go look up the algorithm that applies this. And if I'm interested, I'll go and look at the theory about it. But I'm going to go look up the algorithm that gets it to plot. So I'm trying to figure out which one of these is the best fit. Now that's something the computer, well, it could do, but currently that's something the computer can't do. That's something you can do that the computer can't. Is you're going to plug in all this stuff. You're going to do now I intentionally misordered this because I wanted to get them side by side, but I'm going to run the normal distribution data model. Okay. I'm going to run the log normal distribution data model. Okay. And me using my human brain can say, without even having to run any calculations or anything, that this is better than this one. Computer is not going to be able to do that as easily. In fact, computers are extremely poor at knowing what to ignore. So we're going to do that for the double exponential distribution data model. One thing I neglected to do is I didn't fill in these values here. It would probably help you a lot if we did. So we're going to do that on one of these, but I'm going to finish my thought. So we're going to do the same thing with the double exponential distribution model. We're going to do the same thing with the Pearson 3 distribution data model. We're going to do the same thing with the logarithmic version of that. And then at the very end of what I've done, we got to pick one. So I'm going to say, I think the log Pearson 3 model is best from a visual perspective. You can see that it has the smallest residue. So with that, and this is all hypothetical. I'm making this up. In mind, I went and calculated residues for each model, and the LP3 was indeed best performer. All right. All right, this is me choosing. So what are we doing all this for? Well, I want to be able to predict flow. I want to be able to predict the peak flow for a given year. So, you know, climate change and all that. How much water is the river going to wash away the village next year, based on whatever information we've got? Well, I don't know. Let's get a data model, and let's get a couple data models and see which one's the best. Wheel. I got a couple. And what am I doing? Well, I want to get the best one because I don't want the village. Well, if the village is going to wash away, I want the people to know so that they can not drown. All right, so what's the best data model? Well, I think this one. Why do I think this one? Well, I use my eyeballs, and it seems that the distance between the line and each point seems very small compared to the other ones. So what I'm going to say is this one has the best residue, and by best is smallest. Well, let's make sure. So I'm going to go and I'm going to calculate the distance between each one for this one, and I'm going to just put that into a number. So earlier we were taking a list and we were adding something to an empty list over and over and over and over. And in fact, you probably could get away without actually calculating it. I would want to calculate it. So I'm going to take the residue, 0.1. So our first point, take what the blue dot is and take where at that point, so the predictor value, which is, I think at that point, like 0.001 or something like that. Plug it into your red line, see the value, subtract those two. Put that into a variable. You know, obviously you want to keep the signs correctly. So you could take the absolute value and then do the next one, and then do the next one, and the next one, and the next one. At the end of the day, you have a variable that has your sum of your residues. And if the log Pearson 3 has the smallest residue sum, well, hey, your hypothesis was correct. And as far as I'm concerned, if you come to me with that, like you said, hey, I think the residues are the smallest, and I ran this preliminary, just checking it out, and it appears that way. That's at least good enough to be like, yeah, this looks pretty good. Let's explore it. Okay, so that is what you're going to be doing. I would say, unfortunately, but it's just kind of the growing pains of copy and pasting algorithms, is that we spent a lot of time on the first one, and the second one got faster. And that's kind of how it goes. You'll spend, especially since you've watched me do this, you've gotten some of the growing pains out of the way. What to copy, what needs to be changed, so on and so forth. So for you, I imagine the first one, if you've watched through this, the first one could take, I don't know, 20, 30 minutes. Second one, you're going to be like, oh yeah, this is the same thing, 5-10 minutes. And then the next ones are just going to be wham, blam, blam. Like you'll find where the, so what are we doing with this transformation? We're going to log space. How do I go to log space? Well, I make everything, I apply this function. So I need to find where this function is. And yeah, so that will take me, it'll take me longer to find this, and then we'll to replace everything in here. And that'll be that. Okay, the last thing I want to look at is let's fill in some values for the normal distribution data model. I'm not entirely sure if, because it's in a markdown cell and it's kind of it's the first time I've seen us do this. I'm not sure if filling this in is part of what you're being assigned, but let's assume it is. Okay. So for our normal distribution data model, what is the flow value for the 25th percentile? How would we, and keep in mind, this is the red line. That's the thing we're trying to fit. So how do we do that? how would we get the output value given our predictor value? Well, if that's not clear, let me ask the following. Instead of having something crazy, let's just say I have a function. And my function starts at the origin. It does this. And more than that, I've given you f of x equals, I don't know, 1/3 x squared. Yes, find the value of the red predictor line at the given probabilities. These aren't actually, and so this is the really nice thing. Why on earth did we sort this? It's because now you don't have to guess the date. So I want to know, what's the value at this point right here? Well, what is the red line? What kind of thing is it other than a line? Is it it's a function. Very good. So the red line is a function. And I have a point, an input point. Let's call it, I don't know, 2. How do I figure out f of 2? Well, it's pretty simple, really. F of 2 is 1/3 times 2 squared. It's 4/3. So that's the value. It's what, 1.33 something? So that's the value there. Now, this is a smart design, smarter than I would have been able to come up with. Either Dr. Cleveland came up with it himself or he found it somewhere in one of his old notes, but it's really smart. Why is it smart? Because you're being asked about the quantiles. How on earth am I going to get the marker for 25 percentile? Well, it's right here, 0.25. Oh, I guess it's closer right here. And then where's 0.5? Well, it's right there. And where's 0.75? It's like right here. But the nice thing is you have a function. And what can you do with a function? You can plug in values. So all you have to do is figure out what is my quantile value axis is appearing to be some kind of float. It's a scale from 0 to 1. Okay, so I can put a decimal in there. How can I make 25% a decimal? That's tough. How do I do that? Anybody know? 25% to decimal. How do I do that? What is it?
Divide by 100.
Yeah, that's actually a better way to do it. I was just going to say, get rid of this and move the decimal place over twice, but that is exactly it. Divide by 100, 1/100. So what do we get? We get 0.25, and that's what you plug in. And we have, so what would the 99 percentile be? 0.99. And what would the 99.9th percentile be? 0.999, so on and so forth. So you can fill those values in from there. And let me get rid of all this gobbledygook drawing. All right. So we've got about 2 minutes left. The process of the rest of the steps, we have step A, B, C, and D. What are they? Well, we're approximating, trying to get a best fit. And the only thing is that step A is the normal distribution, step B is the log normal, so on and so forth. So it's going to be a lot of the same. You're going to want your lesson 21 up for some code, because the meat of the exercise is not developing this code, because as I said, we don't need to reinvent the wheel. The meat is, all right, here's how it works for my data set, make it work for yours. As you saw, I probably spent the first 30 minutes like, what do I replace? What do I not replace? So on and so forth. So that's the meat of what you got to do. Additionally, fill in these values as you go. So let's look at the homework. It's the exact same. Well, not the exact same. We're going to do the normal distribution data model first. What's the flow value for the 25% exceedance probability? Well, I'm going to go plug that into my normal, the function I came up with for normal. Same thing with log normal. Okay, that's all I got. If anybody has questions or if Dr. Cleveland has some kind of announcement or something, someone.
I have
Yeah, go
a
ahead.
question. So we have to fill all of these values with the question marks in the homework.
Yeah, pretty much.
Yeah, but I
Okay.
just showed you how.
And so
and-
it's basically 25% divided by 100, and that's how you get that?
Somewhat. That gets you the predictor value. And remember, we have a predictor value and an output value. What you want is the output value. So how do I get the output value from a predictor value? You plug it into the function.
Okay.
Now, the function I gave you was like 1/3 x squared. 1/3 x squared. That is not the function you have. The function you have is what we spent all the time developing. It's the red line. Now it's in here somewhere, but I don't want to give everything away. But the function is in here, and it actually has. It's an acronym, and it has function as part of that acronym, and that's all I will say. Okay. I had someone asking me questions about joining a team for the project. I told them that Tuesday's lecture has that described at the end of the recording. But other than that, I think that's it, and I'm a little bit over.
Okay, very good. Just a reminder, this is the second to last lab that you're going to have to hand stuff in. We have several more labs after exam 3, which inconveniently is Thursday of next week. The next topic that we're going to discuss on Tuesday is classification. Now that can be an entire semester course, maybe 2 or 3. We're going to look at a very simple condensation of the concept. So don't think you will be knowledgeable about classifiers after Tuesday. You'll have just enough to be dangerous, but that's about all we can accomplish in the time we have left. So have a good weekend, everyone. This particular set of problems is very straightforward. Go ahead and use the lesson materials. And I believe Lab 21, the HTML version, actually has completed code in it. That's intentional. And so it should be very straightforward to cut and paste and possibly add a little of your own where you have to be able to complete these two. And this is real data. This is really what data scientists, at least in water world, do for a living. Okay, that's all I'll say. Everybody have a good weekend. And if you don't have a team yet, contact other members of the class that don't have a team and go ahead and put together the team and then communicate to me who your team is. And I don't want you to have teams of one, but if you have no friends whatsoever and you can't contact invisible people, you can do a team of one. Just let me know. All right, that's all for today.
I will be doing all of the grading that I have backlogged this weekend, so expect those.
You're gonna need a lot of coffee, dude, because there's a lot of backlog.
Yep.
Okay, well, very cool. So everyone have a great weekend. Bye-bye. I'm gonna hang up on you all once I figure out how.
Bye.
I do that. I do that. Bye-bye.